Hi everyone. So my name is Amr. Amr, I know it's hard to pronounce, but you can call me Amr, Amir, anything close to Amr. I'm okay. I hope you are still awake. I know it's hard to stay for 2 hours on Monday, but I try to be quick. So I will talk about BeagleBone PRU, which you will use in one of the assignments. I think the coming one. As you know, the IoT requires different level of time. For example, some of them require seconds, microseconds, nanoseconds. So you have to provide different level of synchronization. What we target is time-aware IoT user. What I mean by time-aware IoT user, as Fatima presented, we have this hardware which has a lot of time stamping, registers, all this stuff. We have the kernel, we have the shell and the application, and we have all the way up the user. And now we would like to know what user can monitor all the way up. He will see different accuracy, uncertainty, and stability as he is all the way up away from the hardware. One of the nice embedded platforms is BeagleBone, which you will use or already used in the class. This BeagleBone has a lot of nice features. You can add different OS, and you can choose your flavor, programming language, environment libraries. For example, I will pick something Linux, Angstrom, C++, OpenCV, and then end with a cool application. So it supports multiple things. Also, it has a very nice low-level thing called PRU. Fatima already talked about just a little bit. So PRU is Programmable Real-Time Unit. This PRU, it has capability of accessing the I/O with 200 megahertz, which means that you can execute which means that one instruction will take 5 nanoseconds only to execute. It has a dedicated instruction and data memory, and it has a parallel. It's like a co-processor, as Fatma said. So you have here the ARM side, and you have here the PRU side. And I will compare between the capability of the ARM side and the PRU side. So let's take a look at this PRU benchmark. At this slide, you can see we are writing here in terms of assembly on the ARM without any Linux. In this slide, I'm targeted to compare the ARM side and the PRU side in terms of capability. So in the ARM side, we are writing as low level as we can. So we are writing in assembly without Linux. And on the PRU side, we are using also assembly, which is the common language. And we are only toggle the pin. As you see on the ARM side, you will be able to do it in 200 nanoseconds. You cannot go lower than that. However, in the PRU, you can do it in 5 nanoseconds, which is 40x faster. So this BeagleBone is really powerful, as it gives you high-level stuff, as you can both Linux play on top of that, and it also has low-level capability, as you see here. And PRU is used in many applications: audio processing, real-time sensing, and you can check these papers. However, PRU has a very painful process to play with. You will find that you need to write assembly to play with PRU, and you will find that you will have to go through a very painful configuration process. As I said, there is 2 ways: the ARM and the PRU, and you have to say, okay, this pin is dedicated to the ARM side, this pin is dedicated to the PRU side, and this is a painful process for normal user. If you are expert, okay. I'm not talking about you. So I will talk about user space I/O driver, only to give you the big picture. How we can control the PRU from user space. What's usually happening that kernel will have some complex drivers that will facilitate and give you like high level access to the hardware. So it's like give you high level APIs, and it will do all the complex stuff underneath. This is way of controlling the physical layer from the user space. There is another way that you expose all the registers to the user and ask him to play with it. So he has then a nightmare to like configure all this stuff. He has to take care of it himself, and this is the case for PRU. Everything is exposed to you, and you have to play with it. The advantage of that okay. So the advantage of that the kernel code is hard to debug, so the software code is easier, or the user space code is easier. However, it's not secure, so anyone can mess up with your code. There is something called UIO press driver. So this is a driver which exposes the PRU stuff to you in the user space. Any question until here?
Does Zealand have a working driver?
Sorry?
No, Beagle Bone has a working driver.
No, I am not sure. I don't know. Sorry. Any other questions? Okay. I hope you are still alive. Your face doesn't give me some.
So you're asking Beagle Bone has DMA? Yeah, Beagle Bone has DMA, direct memory access. I haven't checked it, but it should have. I mean, why wouldn't it have? It's a pretty important functionality in Beagle Bone.
Yeah, basically I was trying to do an application where I could get a concept of data and on
How did you do data transfer? From Uspace?
Yeah,
It's part of using DMA.
I knew DMA was here, but there wasn't any driver.
Okay. Yeah, I looked into it.
Okay. Any other questions? Okay. Also, I would like to talk a little bit about bin max, which you will deal with that in the assignment. I am repeatedly saying assignment. I feel that people wake up when I say assignment, so you will make use of it. So, you know, the hardware support multiple functionalities like CAN, PWM, EDC, all this stuff. And it doesn't make sense to have like a dedicated bin for each hardware. So what they did, they multiplex the bin. So it has an advantage that you have lower number of bins, but on the other hand, you cannot use all of them at the same time, which is the general case. No one will use all this stuff on the same time. If you need to do so, you have to do your design from scratch or use multiple of them. So the Beagle Bone has something called bin max. That's something like this figure. It's not like that in reality, but it's something like you choose the mode of the bin based on your needs. So you have to make sure that you put the bin on the right mode before you move on. This table is pretty popular in Beagle Bone. If you would like to play with, I think you need to do so in the assignment. I here cut part of the table, you will see there here is the bin. On the BeagleBone there is two sides, B8 and B9. For example, here I'm talking about B8, and each bin will have a dedicated address and multiple modes, up to 7 modes. Not all of them will have the seven modes, but some of them will have 7 modes. For example, if I would like to say, okay, please use bin 811 to the PRU 0, I will say something in something called overlay file. I will give it like the address. If you go to the address of 811, which is here, you'll see the address is 34, which is here, and then you will say, okay, I need mode 6. So this is like a big picture of how you write the overlay, and you will find a lot of examples online for this.
So is the first line of code the same as the last line of code, or just different ways of doing it?
No, this is the same file. This is one file. You have to specify all of these.
But why does so what does the first line of code do?
It's here you only write the bin name. I'm not sure how they combine the file. I only understand how to use it. So you have to do so and specify here what you will do, what you will use, and here is the address, and here is the mode. Yes. But it's specified for BeagleBone. It's not for anything else. So all of these only for BeagleBone. And this table is for BeagleBone Black.
There is a folder called documentation, and under that we have about data. We can see something like overlay notes and all of them. They're all in the
Thank you. So you can check a lot of examples online, and you will get better understanding. So let's take a look of how PRU think about time. As I said, there is hardware, there is kernel, application, and there is user. And the PRU setting on the hardware side, and the user is all the way up, seeing the Linux time, which Fatima described using get time, get resolution. All of this is Linux time, but the PRU is totally hardware time, or like a counter value. So the user will be confused between this. He would like to make use of the low level capability, but he has another notion of high level time. So how to solve that? One of the popular examples of using the PRU is the inverted pendulum. I think one of the projects here will end up with building inverted pendulum. I hope they succeed. So for the inverted pendulum, you will have, all of you know the inverted pendulum? Anyone doesn't know what inverted pendulum is? Okay, so inverted pendulum is something that you would like to keep up. And we will connect the inverted pendulum with BeagleBone. This is the setup in our colleague lab in Santa Barbara. So the idea is they have the controller on BeagleBone Black, and they have the system, which is the inverted pendulum. All of you are familiar with this loop, control loop, BID. All of you are familiar with it? Okay, so it's a very simple control loop. You have controller, you have system, and now the PRU will come on the picture as you would like to do a precise action with low level stuff, but you are on the Linux side. So think about this controller would like to take precise action using the PRU, but the user is is sitting on top of the Linux side. So he would like to make use of the PRU. I'm giving this example as to motivate using of PRU. Here is a video to wake you up. It doesn't work. So here he make use of the PRU to control the inverted pendulum and make precise actions. So as you see, it can stand up, and there is a lot of research showing the effect of being asynchronous, like doing asynchronous action between the control side and the process side. So it's very important to do precise actions and to be synchronous. Okay, let's continue. So you will deal with a framework called Cyclops in the assignment. So the idea of Cyclops is to help you in automating the configuration. You don't need to do all the painful configuration stuff, and it provides like open source JavaScript inspired language to program the PRU. It also has a browser IDE for prototyping on PRU instead of using low-level stuff. It provides some APIs to do some common low-level stuff. There is another way of dealing with PRU. Instead of writing assembly, there is a TI compiler where you write C. However, it has advantage and disadvantages. The advantage that you will not write assembly anymore. However, you will write C with over a closed compiler. So you will use the predictability of the time on the low level. So you will not reach the 5 nanoseconds, which I showed you at the beginning if you use the TI compiler. However, again, it's a C, so it's a trade-off. So Cyclops takes the advantage of both. It provides, yeah.
Why can't you get, if in C you just directly like XOR a register or a memory location that maps to a register, and then get converted into assembly? Why would you not be able to get 5 nanoseconds precision? What is the compiler add that makes it?
You mean write assembly in C?
Well, even just a C line. So let's say you have the same register that you're toggling in assembly to make it go up and down.
Okay.
Toggle in C with just an XOR.
But you don't know how the compiler will generate the code. For example, if I say for loop or while something, wait for some time, then toggle the bin, something like that, you don't know how the compiler will do it. Every line of code matters now. You are talking about very precise timing action, 5 nanoseconds. So you don't know how the compiler will do it, and you don't have access to the output also. So you have no idea what will happen. And we will see here an experiment of that as a disadvantage of using the TI. Also in Cyclops, we will be able to do like time synchronization between the Linux side and the PRU. I would like to say that this PRU is out of one of many projects, very talented students, and it ended up in a paper. And also there is another paper out of many classes. There is a lot of papers goes out of many classes. So try to do as good as possible. I mean, a lot of projects has a lot of good ideas, which can end up in a research paper. So do all your best and good luck. So here is the Cyclops IDE. He depends on one of the open source IDE. Here you can write the Java inspired language, and here you can press compile. You will get the errors here, warning, and here you can see the generated output. And now you can play with the generated output, comment one line, replace it if you don't like the compiler behavior. So as you see, it has a very great advantage that you have access to the output, play with it. So here you have full accessibility to the output of your compiler. This is the Java-inspired side of Cyclops. It's not TI compiler anymore. Okay, you got it? For Cyclops, it's only a baby language still. So it has variable assignment, direct reading and writing to bin, arithmetic expression, condition statements, loops. To give you some intuition, don't think this is an easy thing. I was impressed that most of this work is done by only one person in like 2 or 3 months, and all the, as I said, the PRU is written in assembly, and now we are doing this over a high level language. You know how assembly is painful in programming. Now when it comes to the TI side, we provide also some APIs over the TI side. So for example, if you would like to play with EDC, you can call only this API, and instead of configure it yourself, you can read the EDC, read bin, assert bin, toggle bin, only APIs. And you don't need in Cyclops to configure the device overlay. It will automate the configuration, so you don't need to configure anything. Once you write pin 1 equal 1, it will understand that this pin is used as an output, configure it as output, assign it to the PRU. All this is underneath. Any of you knows how to do time synchronization between two sides? If you have clock and she has clock, how to do time synchronization?
So you can send you have a communication between the two, right?
Yeah.
So you can send a packet that includes what time you think it is right now. At the same time, you start your own timer, and then you wait for a response from the other side to get back to you. You timestamp that one as well, and you stop the timer, and you measure the difference between when you sent your packet and when you received the packet back. And the person that sent the packet back has also inside of that packet what time they think it is when they got it. Subtract the difference and add your timer value. Not the most communication that's happening either, right? Because if you have like an user communication, that wouldn't work anymore. When you send the person, then it doesn't keep moving. So it depends on if you want it to delay or not.
All of you are right.
Yeah.
The things that you said was also right, and you also have to take care of the property delivery, the time the packet spent in the medium, starting from you to the other.
I have only one comment on and how you describe it. You are not calculating the offset between sending and receiving. When I'm talking about time synchronization, I would like to know if I am saying 1 p.m., what's 1 p.m. correspond to your side. For example, if I say to you, what's time in UTC, how you can transfer this to like BDT, GMT, anything. This is time synchronization, that you understand the offset between the two time entities. Okay, so this is the big goal of time synchronization. Now, how to do it? This is my question. There is multiple ways. The easiest way is to do only one message, like this. For example, this is the master node. Well, the time at the master node is 3 time. For example, time equals 3. And he will send to the nodes, okay, my time is 3. Now, every node will build a table. What's my time at 3? Now, this node, its time is 15. So now, repeat the process. You will have a table of mapping. Now use some functions to map from this time value to this time value. The easiest thing to calculate the offset, okay, the offset between them. Sorry. between them is 12 or something, and add the offset, and that's it. So you need to calculate the offset between the two nodes, not the offset between sending and receiving. However, to clarify, when people need to do two-way, if you need to do two-way, you are talking about calculating the propagation delay. As I expect from you when I describe this process, to say to me, okay, 3 is not corresponding to 15, as there is propagation delay time, right? Do you understand this? What time synchronization? It's like a time stamping a common event on the two sides, right? Yeah, propagation delay, you need two-way. You need two-way messaging, and there is a very popular formula to calculate it. Only take the offset, as he said, something out of it. I can post it to you. So, yeah, I think there was a lecture about that.
He said he hasn't given it yet.
Oh, okay. Yeah, so in order to calculate the propagation delay, you have to reply back. And you will have now 4 time stamps. Receive, send, receive on both sides. Now you will be able to calculate the propagation delay. However, a lot of people assume the propagation delay is constant, and they will deal with this structure. So I receive it at some time, take out of it a constant value, and then play with it. Now, why I said that? As I like to describe how we do the synchronization of PRU with a Linux type. So the big picture of time synchronization, you have 2 entities, and you would like to know to timestamp a common event on the 2 entities. Are you still awake? No? Okay. Okay, let's see. So we have PRU, we have the ARM side, we have kernel on top of the ARM, we have the user space on top of the kernel. And now we would like to synchronize this guy with the PRU. So we will connect physically one pin from the PRU side to the ARM side and assert this pin. This is like a common event. So what do you expect me to continue? What do you need from me now to do time synchronization, given that I will do this assert pin? Can anyone guess? What's time synchronization? Any idea? No, don't talk about how you will do it. I'm talking about, I would like to synchronize 2 entities, and there is a common event. I would like to continue now in describing. What do you expect me to do now? I said to do time synchronization, you need to do common event and time stamp it on both sides, and then do calculation to match them, right? So what do you expect from me now? Any idea? Phone? Say whatever. Manny is not here. However, he can see the recording. So what do you think? So I would like you to get the big picture of time synchronization. If I ask you to do time synchronization between 2 of us, how you will do it? Exactly, you need to timestamp a message on both sides. So now this is my common event. I expect to get the time of this event here and the time of this event here, and do the mapping. See how simple it is, right? Yes? Okay, let's see how to do it. I now assert the pin from the PRU side to the ARM side. The PRU will read the time. Of course, it's not it's not accurate as it executes every 5 nanoseconds. So you already lose some time here. Then the PRU will convert this value to nanoseconds. As Fatima said, you are reading a counter value. So you need to map the counter value, deal with overflows, and map it to nanoseconds. Now the PRU is done. Let's see on the ARM side, which is a scary side as it has ARM kernel user space. You will find that the ARM has some low-level capability to capture the time. Low-level capability, it means when I toggle a pin, it can take a copy of the counter in hardware. So it will capture the time, send it to the kernel. We have here kernel module that converts this value to a nanosecond. Then we will send this value to the user space. Now the user space will send back this T4 to the PRU. Now the PRU has two values, the T4 and the T2. Now it's the two timestamps of this common event. Now the PRU can get and adjust the time. Anyone understand anything? I mean, if I tell you the time now is 1 p.m., you can add to it and do some calculation to get the time on the other side. So if I tell you 1 p.m. at GMT, can you calculate the time at UTC? If you can, now you have the transfer function of time synchronization. So yeah.
So if they have a delta, so let's say you have two parallel clocks running, and one thinks it's 1 p.m., one thinks it's 1 p.m. 1 minute. So they have a 1 minute delta. That's what you're trying to correct here, right?
Yeah.
Okay. So you would basically not only timestamp that, but read whatever the timestamp of the other side is, which is contained inside of the packet, right?
Yeah.
Okay.
Yeah.
In this particular case, there's no packet exchange. PRU and ARM are on the same platform.
Oh.
The common event which we are generating is that we connect two pins. One the PRU pin, ARM pin, and they both are getting a common signal, an external common.
But there is still this is a message exchange between the kernel and the PRU side, right?
Yeah, same platform.
Yeah, it's on the same chip, yeah, but they are two entities, right?
So, like, how do you send is it a one-bit message then? Or is it just a one pair?
There is a kernel module that play and let you send from PRU to Linux, and you will play with that in the assignment. So it will let you deal and send and receive message. Any more questions? So this is like the architecture of Cyclops. The blue parts is for the Java-inspired language. You will see here is IDE, here is PRU, and some stuff in the user space, some stuff on the kernel. The red boxes are for the TI compiler. This is the UIO driver, which I talked about, to expose all the registers of the PRU all the way up to the user so that he can play with. So let's take a look of how to generate pulse width modulation using PRU. This is the original language of PRU, which is called Bazel. You write some assembly and configure everything by your hand, write the overlay file, all this stuff, compile all, do all this stuff. On the other side, you can do this with Cyclops in the C library using the API, like assert pin, wait, deassert pin, and that's it. And here, he will understand that you will use this pin as an output. You don't need to configure anything. If you use the Java-inspired language, also here you can set the pin to something, and he will understand it's an output and automate the whole process for you. You don't need to configure anything. And the tick here is like the counter tick. Wait for some time, then toggle the pin. This will generate some pulse width modulation, up high, with some width. Okay, I would like you to tell me how to evaluate time synchronization. I assume that you understand how to do time synchronization. Now, if I claim to you that I have 10 microseconds time synchronization, how you can evaluate me?
So you can have them both at a predetermined time, have them both toggle a pin high, and then have the two pins coming out in the oscilloscope, and you can see when they both go up and see how different they are.
Okay, this is
if they're truly accurate, they'll both up at the same time. If not, they'll get slight delta between them.
Okay, this is one way. Anyone would like to suggest another way? You would like to suggest? So what he said, can anyone repeat what he said? Come on, guys, I have finished, so only repeat. So do you understand what he said? So what he suggested?
At a predefined time, like you decide that both the processors are going to give out a particular event, trigger an event at a particular time, and then you observe if both the processors are triggering the event at the same time. And if there is any delay, then it's present delay. Otherwise, they are accurate.
Okay, so in other words, he is saying we agree to generate an event at 5 p.m. and then on an oscilloscope see the difference. Okay. This is one way of evaluating the time synchronization. Can anyone suggest another way?
Compare the timestamp of a bunch of events and see if they match the same.
Yeah, can you explain more?
If you have events that's occurring on both processors, you just, like the whole picture, you just look at the timestamp, and if one's 11 and one's 15, then they're not.
Exactly. So this is another way. Yeah. Exactly, yeah. So what Liam suggested, to have something monitor the input to the output of the system, like do something at 5 p.m. But what he suggested, so what's your name? Jay. So what he suggested, to have someone monitor the input. So I will do events, you will tell me the time, he will tell me the time, I will compare. So this is two ways of evaluating the time synchronization. Here, what we did, we generate an event on both sides. So we used your idea of generating a common event and compare the time between the two sides. And this is the synchronization error. It's in microseconds between the two sides, given that the synchronization period is 32 seconds. So every 32 seconds, I will repeat the whole process of exchanging the timestamp. Or why I repeat the whole process, can anyone guess?
So oscillators aren't perfect and will drift, then you gotta keep
Exactly. The clock are drifting, there is a lot of environment factors, so you need to repeat the process. So you would expect if I repeat more, I will be more accurate until I saturate to some level. Here, if we do the synchronization once, you will see it's worse than before, which is expected, as when I do more, I will be in a better shape. This is the latency for doing read PRU time. So read PRU time requires 600 nanoseconds, and adjust PRU time requires 2 nanoseconds. Read time requires 115 nanoseconds. Now I give you the answer. Let's return back. I expect any of you ask me why you didn't get perfect synchronization. You are on the same board, claim that you are a great person using PRU, Superman, and now you are talking about microseconds, not nanoseconds. Can you tell me why? Why it's not nanoseconds accuracy? First, do you understand this figure? All of you understand? No? Okay. You already said the idea and you didn't understand this. Okay. So I generate here a common event, and the PRU, one bin is configured. Yeah. So one bin is configured to PRU, one bin is Linux side, and then both of them will timestamp and to do time synchronization to compare. And this is the synchronization error between the two sides. Okay, so my question now, why it's not 0? Why it's not nanosecond? No, it's not 0, it's microseconds. When you are talking with time people, microsecond is bad. No, it's 500 nanoseconds. Yes, but it's not nanoseconds, it's microseconds order. This is how you can fake people in rewriting papers. You can write nanosecond and then suddenly on the scale write 1000. It's not nano, actually it's micro. I mean micro order of magnitude, not nano. Yeah, why it's not 0? Yeah. Yeah. Yeah, listen this. How we do time synchronization? Again, let's repeat to the original problem. How I do time synchronization? I will do an event. I will tell you this is my time, this is your time, and then we will compare. So when I tell you my time synchronization is not perfect, so what do you expect? There is a problem in this process of generating and comparing time. When I generate, am I accurate in generating? And when you capture, are you accurate in capturing? And when we send, is there a delay in sending? This is all the sources of problems in time synchronization. And I already cheat you and give you some hints and no one take it. I'm telling you this is the delay in doing the APIs of reading the time, adjust the time, read the time again. All this stuff has a lot of latency, so it's not accurate. It's not fixed. It's like mean. So did you get an idea why it's not perfect synchronization? And now return to Leon's question. This is over the TI, which is a closed compiler. So we don't know why it's such a huge latency, as it's a closed compiler. I hope someone of you like Cyclops and do it on the Java-inspired language. I am sure you will get much better than these results, as these results over the TI compiler. Do you understand?
I have a question. So if it's a closed compiler, does that mean you can't read the assembly output that it generates?
Yeah, you don't know what's going on. What?
You still read the sample output?
No, I don't think you can see the output. It's like binary. Do we have time? Little bit. Let me show you the Cyclops repo as you will play with it. I will open. I don't think so. You can see the binary only. I am not sure if it's possible to do so or not. But also, I am not sure if the result will be readable and you can modify it. Yeah, maybe if you consider extra process like that, you may get better result by enhancing the output. But here we are using it as a black box. We didn't modify the output. We just depend on the output, write as clean as we can on high level, and that's it. But you can consider clean it more. Do you got my point? You understand? I'm talking to you. Yeah. Yeah. Guys, can you be quiet a little bit, guys? Can you be quiet? We need to hear him, right? So you are saying that there is a problem, and yeah, I'm saying you don't know what's going on. We just depend on the output, run it, and that's it. So we didn't consider try to hack it and see what's the assembly, fix the assembly, all this stuff, see where is the source of error. Yeah, we didn't do that. You can play with it, inshallah. Yeah, we treat it as a black box. So in the assignment, you will play with this Cyclops. It's under the NSL. I think Professor Manny will post for you the slides, so it will have the link. You will find here 3 folders. The C library folder, and it has examples to play with if you would like some hello world examples. There is a Java inspired side, which is the IDE. It has some instruction how to run it, all this stuff. And there is a full image if you would like to build an image, as this work is only compatible with one kernel. As you know, Linux has a lot of nifty stuff. If you change the kernel, a lot of stuff will change. So this work is only tested on one kernel. So we recommend to use the same version and the same image. So these are the references for the presentation and some figures that I borrowed or stole. And thank you for your time, and send us. Thank you, guys. Send us messages. Our emails, I think, are on NSL website, so you can send us message whenever you want. Thanks for listening.